Hello, welcome to this abstract with the number 3129, and this is a collaboration between many scientists and many labs, and I have no financial interest to disclose with respect to this presentation. Summarizing this abstract, we are looking at Layer-fMRI acquisition protocols in the lower half of the brain. And there are many advanced and routinely used methods out there. We tested all of them and find that almost none of them really help. We are better off by using minimal grappa, not using PTX, not using advanced shimming methods. Only these kind of dual polarity EPI readouts seem to be very helpful. As introduction, I care about this field of layer-dependent fMRI, which is an emerging field with an increasing number of papers that going across more and more brain areas, with about 96% of all the layer-fMRI papers looking at the top half of the brain. There's almost no literature in the bottom half of the brain, despite the fact that there are many relevant layer questions to be asked down there. Just to name a few, you can look at these small structures like the amygdala and their subnuclei for emotional or face perception. There's FFA-PPA to look at hierarchical processing of faces and places across feed-forward or feedback projections. There's hippocampus and memory-related area that are known to encode memory retrieval or encoding of memory in the different layers of the cortex, and there are also these superior cuniculi, the small structures, and also in the cerebellum, the motor function. All of these things are very interesting and need high resolution. Most importantly though, also the lower brain area are the kind of problem child of whole brain layer-dependent fMRI. I've invested my last 5 years on whole brain readouts with continuous improvements of sensitivity and acquisition speed, and also with connectivity maps that I'm kind of proud of. But still, down there, it's like a jungle. It's messy, there are artifacts, these wiggles, the TSNR is bad, and also these kind of phase inconsistencies. So it's too messy and too noisy still to have tools that can be disseminated for standard users. And the reason why it's so hard down there is multifold. The TSNR, which is usually okay up there for high resolution, it's kind of horrible down there. The transmit efficiency is okay up there, but it's very hard to get good flip angles down there. Geometric distortions are kind of manageable, even with the low bandwidth of layer-fMRI. Down there, it gets really, really bad. Most importantly though, for layer-fMRI, we need to have large matrix sizes, so we can kind of use these tangential field of view prescriptions where we can reduce the field of view a bit. In the bottom half, no matter where you are, you need these giant matrices of matrix sizes of 300 and more, and you cannot acquire so many k-space lines before the signal decays away. This is a challenge. There is a lot of literature out there describing these very challenges and also potential solutions. And there are conventional themes, like for example, the challenge of undersampling, PTX, there's a lot about distortions, B0 inhomogeneities, advanced trimming methods, and also brain motion and physiological noise. Almost none of these papers, though, look on submillimeter fMRI, on layer fMRI. So the goal of this abstract is here to pick the approaches among those that look most promising, implement them, and optimize and validate them for layer-dependent fMRI in low brain structures. So in the following, I want to report on our attempts to work on these 5 different issues, starting with the matrix sizes. Since we cannot restrict the field of view at low brain structures for layer-dependent fMRI, we need to acquire large matrix sizes. And it just takes a lot of time to go through k-space back and forth and back and forth and back and forth. And this gives the readout time to accumulate phase errors and also have signal decay. So we need to be faster and subsample our data. Meaning that we are only acquiring a subset of the lines, and then we need to fill in these other lines by other means. And there are 2 different approaches here. One very common approach is to use grappa and fill in these missing k-space lines. Another approach is to acquire these missing k-space lines in the next shot or in the next CR and then combine them. And those 2 approaches are kind of combinable, but they're also in competition. So it's not really clear how much we should push on grappa or segmentation. And here I'm showing you a high resolution protocol in low brain structures, looking at either not using grappa at all and a lot of segmentation, or using a lot of grappa and no segmentation, and then combinations in between. And you can see that the extreme cases are kind of not very efficient. For example, if you don't do grappa and only segmentation, you can see that even at these high resolutions, we are physiologically noise limited. We have these shot-to-shot phase errors, especially also motion around the large vessels and so on. So our TSNR is not the best. If we do a lot of grappa, and no segmentation instead, we not only have a lot of G-factor penalty, but also we don't have enough coils to really unalias those images, so we have a lot of artifacts. If you go a bit easier on grappa, you can see that those artifacts go away. However, still we have this noise amplification from the G-factor, and this is something you never get back, even if you average the more samples that you have. So the TSNR efficiency is quite bad if you're too liberal on grappa. So a combination of those where you are very conservative in grappa and more liberal with segmentation might be a kind of optimum. And this obviously depends on the area, specifically down there in the brain, but also on the resolution. So for example, if you push this more to the lower resolutions, you can see that the optimum shifts a bit further towards the right, where it's still beneficial not to push grappa too much and use a bit of segmentation, but then you can lean a bit more towards grappa. And finding a good compromise between undersampling patterns as well as multi-shot methods, I think, is the common theme of the field of acquisition methods in layer-dependent fMRI of the last decade or so. So we find that usually it does not make sense to push grappa too much, but also add a bit of segmentation in there always. With the large matrix sizes at high resolutions down there at these low brain areas, we are also challenged with the fact that we must do a lot of ramp sampling at these highest, most ambitious gradient forms that the hardware allows. So I end up with these low spatial frequency fuzzy ripples, like in those examples here in this multiband sequence. The dual polarity grappa approach from Hoke and Polymeni can really nicely mitigate off-resonance effects, for example, up there as promised. However, there are still these kind of shading patterns in there, and also a bit of cost in TSNR. Similarly, also in 3D EPI, that it's inherently kind of more robust to these off-resonance effects over there. You can still see these fuzzy ripples quite a bit, specifically if you inverse the read directions and basically invert these low spatial frequency ghosting patterns. You can see that there's still a lot of artifacts in there. So to combine those two different readout polarities, you can see that then it takes care of both the off-resonance effects as well as these fuzzy ripples, as we call them. So we find that these like dual polarity readout calibrations or acquisition approaches can be very helpful to deal with those kind of fuzzy ripples, these shading patterns that most people are very familiar with that are working at high resolution low brain fMRI. Next, let's look at the challenge of geometric distortions. You know that fMRI at high field strength is challenged by B0 inhomogeneities, especially at the low bandwidth of layer-dependent fMRI. And these inhomogeneities are coming from dipole perturbations at susceptibility borders like at the ear canals, especially affecting these low brain areas. And from this cartoon you can see that the gradient perturbation is highly directional dependent. So there's a strong gradient of the perturbation in this direction, and there is a weaker gradient in this direction. The Shim tools from our Siemens vendors appear quite outdated compared to the solutions of the academic literature out there. And there's this well-reported issue of having kind of this weird gradient residual of in this anterior-posterior direction over there. So we tried to see if we can reduce these effects of the distortions by using the advanced Shim software from the Resonance Research Inc., which indeed got rid of these gradients up there. However, it turns out that there's also maybe a tiny bit of compromise, specifically at this prefrontal cortex over here, that looks like there's even more of a distortion field in front there. And overall, the distortions are kind of not that bad in the slab, kind of going through the lower part of the brain, for like a typical slab as you would use it. So I found that it's not really worth the trouble to buy extra software and dealing with sending raw data off and then on the scanner. So at the end, I found it most efficient to just optimize the read direction in the direction of the strongest gradient. So while being liberal also with segmentation. And then you can see that you can even get a signal back from these like very challenging areas, for example, the entorhinal cortex right above the ear canals. In case you worry about these issues of geometric distortions with respect to errors in layer segmentations, I also want to refer you to abstract 885 from Kenny about the nice protocol that's called T1234 that acquires a whole brain EPI T1 weighted scan in the same distortions as the functional scans in just 3 minutes, including not all but many of the low brain areas with the distortions that you need. Another very prominent theme in the literature of low brain imaging at 7 Tesla is PTX, which is now straightforwardly usable on the Terra scanners and even FDA approved on the Terra X. So I was particularly excited by the sales pitch of PTX via the universal pulses that turn an MP range image without basically the lower brain structures into something with the lower brain structures. This is something I want. Also, the transmit part of the coil just looks better on the PTX compared to the STX. Whereas, however, it's not really clear if this is really the active elements, the transmitter, or if it's just bigger because there's more electronics in there, if the casing is just bigger. So our empirical tests were a bit disillusionizing though. So for example, just using the B1 Shim only, you can see that yes, the B1 is kind of shift around a bit, and maybe at the pole of the occipital lobe there's something different, but overall the cerebellum still looks kind of dark, and the bottom of the temporal lobe still look just as dark as before. And after all, I think it makes sense because these 8 transmit elements that we are having are kind of aligned in one single row. So there's not really a degree of freedom at all to push kind of the field down. There's not a degree of freedom in the up-down direction to begin with. All the improvements that we are seeing here from the universal pulses then must not only come from the PTX alone, but mostly also from the gradients, from the KT approach of using gradients during the excitation pulses. The most concerning results, though, that we found by comparing the STX with the PTX coils was that for highly accelerated images that we need to acquire in layer-dependent fMRI, we always found a higher G-factor penalty using the PTX coils as opposed to the STX coils. So here you see that the G-factor can be significantly higher, like 20 to 50% depending on the area. And actually this is not really limited to layer-fMRI, also for kind of any other highly accelerated imaging protocols. For example, here just looking at the UK70 standard protocol, you can always see that the G-factor penalties are always higher on the PTX coil compared to the STX coil. And I've talked to the vendors and I talked to many labs that are experts in PTX imaging without really a clear answer. Some people acted like I'm crazy and this shouldn't be because the same receiver hardware is used, right? The only thing different for PTX is the transmitter. And some other people say that this is absolutely expected. And they see it too, but there's no public discussion about it at all, which was quite frustrating. After a bit of getting lost in the details, I think we came down to kind of that it's mostly coming from noise coupling. Having more independent transmitters close to the receiver makes the noise in the individual elements just more coupled. So across the different scanners that we looked at this, we always found that the noise correlation matrix is weaker for the STX coils as opposed to the PTX coils, where the noise coupling was in some scanners really, really high, consistently higher than STX. So I came to the conclusion that PTX is not really the way to go with the standard hardware that we are all using, at least not until universal pulses support the fMRI as promised in previous abstracts. So I'm looking forward to also using slab selective universal pulses for fMRI. So next, let's look at the concern of high resolution fMRI in low brain areas with respect to brain motion and physiological noise. Like for example, in this tweet from my boss, the NIH director, they deceptively show that the brain would be quote unquote a moving organ. So they're using a motion amplification model of the synthetically amplified cardiac motion based on a low resolution distortion field. And you can see that it looks horrible, right? How can you ever do layer dependent fMRI with these kinds of motions? So to quantify this effect and this problem for layer dependent fMRI, I took a protocol that we would use, for example, a 3D EPI protocol, with high in-plane resolutions looking at the brainstem. And you can see here that there's a lot of stuff going on, right? There's kind of these kind of stark shading patterns moving up and down. It's not really clear if the brainstem is actually moving though, which might be better visible here, for example, looking at the mean in the underlay and then the cardiac induced motion as an overlay, where you can see that the mean is crisp, like crazy. There's no real blurring at all. You see these very tiny stripes patterns, these anatomical features, and also the cardiac induced motion and signal changes. You can see that they are not really within the tissue. You can see there's a lot of signal changes around the brainstem and the vessels, and you can see that there's CSF kind of flushing, and this is maybe even better visible when you go to longer echo times, where you can see that the CSF is really flushing through and then even going into the sulcal space over there. But overall, it does not seem like the tissue borders of the brainstem seem to be moving a lot. And the CSF rushing is rather kind of within the ventricles over there. So I find that the brain tissue is not really moving as much as people are afraid of. So a solution to all this kind of physiological noise down there is just to increase the resolution and then restrict the motion into the voxels and the places where it should be, namely outside the tissue. The tissue itself does not seem to be moving as much. Next, let's look at the third order Shim. The field has learned from Nicolas Boulant recently that the third order Shim can induce issues in the gradient waveforms. The gradient impulse response functions are worse with the third order Shim. So we were wondering if this also can have an effect on EPI and the artifacts that we are seeing in the low brain areas. And we know that a nominal EPI like that is usually not really ending up being played out as nominal as this one. Namely, we usually kind of cut the corners of these trapezoidal shapes. And this is happening right during image acquisition, like during the data sampling when we do ramp samplings. Specifically, these errors are usually at the kind of corners, and therefore they are kind of spiky, they are sparse along the readout. This means that we are not getting a nominal EPI trajectory like that, but instead we are getting something like this, where we start regularly, slowly, then we kind of have a delay, we never really catch up, have another delay, and then go back and forth and back and forth and back and forth. So we have kind of these odd even line shifts that are different for high spatial frequencies as opposed to low spatial frequencies. And depending on the phase correction, then we end up with ghosting patterns in the low spatial frequency domain. For example, looking like this, these kind of fuzzy ripples that most of the high resolution Layer-fMRI folks are familiar with. Now, the thing that we are flipping back and forth here is having the third order Shim connected and having the third order Shim not connected, specifically disconnecting it inside the Faraday cage to minimize kind of coupling, capacitive coupling of the third order Shim with the gradient. And so you can see that the EPI image quality looks much better without the third order Shim, but let's also look at this here, for example, for a functional activation, where you can see that in the movies with the third order Shim connected, there's a lot of fluctuations going on. We have these fuzzy ripples and they basically destroy our auditory activity, which is not really very deep in the brain, but it's kind of borderline between upper and lower part of the brain. And you can see that there is activity where we would expect it. However, it's not at all as beautiful as for the case where we have the third order Shim disconnected. And to show you another example how reproducible this is, here again we see these fuzzy ripples when the third order Shim is connected for another person now, and you see that in the unthresholded activity maps there is activity going on. However, it's much weaker and it's kind of hidden under these fuzzy ripples. So only part of the area exceeds the detection threshold, because everything else is hidden in these fluctuations of the fuzzy ripples. And obviously this effect is highly frequency dependent for a given echo spacing. So here, for example, you see that we never really have a disadvantage by disconnecting the third order Shim. The data always look better for these protocols with the third order Shim disconnected, but there are some protocols where it doesn't really make a huge difference. There are some frequencies, for example this one or this one, very close to the mechanical resonances, where we have worse fuzzy ripples, which might be better visible also here looking at the zoomed section of these very data. The surprising thing for us was that these fuzzy ripples are not always largest when we are close to the mechanical forbidden frequencies, these echo spacings that we know are not allowed because we have these mechanical issues of the gradients. But sometimes the strongest effects are actually far away. And we believe this is mostly coming from the fact that an EPI is not really describable by a single frequency of the echo spacing, because we have these trapezoidal shapes that are not describable as a kind of sine wave. This means that we have these sidebands and we have higher order harmonics, and in this example where the main echo spacing is actually just outside the forbidden frequencies, you can see that these peaks of the sidebands are actually already inside the forbidden frequencies. So therefore we also have these issues of the fuzzy ripples when the third order Shim is connected, when we are not really hitting the forbidden frequencies. Considering all these lessons that we have learned from this, we tested a number of protocols of some high-resolution applications in the lower brain structures that I would like to show you now. The first example is the amygdala, which is sensitive to kind of emotional phases, specifically in the basolateral subnuclei. So here we got good activity by using these dual polarity approaches, as well as using a sagittal approach compared to the axial one to benefit from the lower distortions there. But then we were still a bit worried about this blurriness and the distortions up there. So in the next study, where we focused on low brain structures, even deeper structures, namely the superior colliculi, we are using even more segmentation, additional in-plane segmentation, to end up with a total segmentation factor of 6 that ended up giving us very nice TSNR maps and also activity in the areas where we would expect it, namely part of the primary visual cortex, but then also the superior corniculae. Going even deeper here into the cerebellum, looking at kind of motor function, we found that it's even there helpful to use very aggressive segmentation. So again, here we are doing a lot of segmentation while also using this kind of dual polarity approach that I showed you. Even more challenging in the neocortex, right above the ear canal in the entorhinal cortex, over there we are looking at layer responses for memory encoding and memory retrieval for repeated movie watching paradigms. And there we do get weak but consistent layer specificity across the different cortical layers. Also looking at the hierarchical processing of FFA PPA, we get somewhat reliable activation maps of houses versus faces in different feed-forward or feedback signatures as expected. In conclusion, 7 Tesla layer-dependent fMRI in low brain area is not good enough. It's hard. It's hard for conventional fMRI, but it's even harder for layer-dependent fMRI. There are several methods available that have potential to help, and here we tested all of them for the purpose of practical applicability too, and we find that it's not really helpful to use very liberal grappa, PTX, or third-order shimming. Instead, there can be even counterproductive. We found it more helpful to use liberal segmentation and the dual polarity. And with this, I thank all my colleagues, and I thank you for your attention.